All right, today we are diving deep into the world of tool steel. We're going to uncover the amazing recipe of, well, fire and ice that takes a regular old piece of metal and turns it into something with incredible strength and resilience.
So here's the big question, right? How in the world does a simple piece of metal become a super material? I mean, how do you take a chunk of steel that's soft enough to cut and shape and turn it into a tool that can do the cutting for literally millions of cycles without breaking down? Well, the secret isn't just in the metal. It's about sending that metal on a journey. And believe me, it's a pretty violent but very controlled transformation. We're talking about changing it right down to the atomic level. So let's follow that journey together.
First up, we're unlocking steel's hidden power. The journey, you could say, begins with a whole lot of untapped potential. You see, in its raw state, steel is actually machinable. But its real strength? It's locked away deep inside its atomic structure. This initial state, what we call annealed, is super important. The steel's atoms are all nice and relaxed, which makes it soft enough for us to machine it into, say, a complex die or a sharp cutting tool. But here's the catch. In this state, it's pretty much useless for any real work. All that strength is just hiding in there, waiting for us to unleash it.
So to get that strength out, we have to go deeper. We need to completely rearrange the building blocks of the steel. This is the heart of the whole process. We're talking about atomic transformation. Okay, so the first thing we do is heat the steel way up, past a critical temperature. This forces its atomic structure to change into something called austenite. Now, the best way to think about austenite is like a sponge. It's this high-temperature state where the atomic lattice opens up and can just soak up carbon atoms. And carbon, well, that's the magic ingredient for hardness.
And this is what we're aiming for, martensite. Once our austenite sponge is full of carbon, we cool it down, and I mean fast. We quench it. This rapid cooling essentially flash freezes the atomic structure into this new form, martensite. All those carbon atoms get trapped inside, twisting and distorting the atomic lattice. This creates a ton of internal stress, and that stress is where the incredible hardness comes from.
But wait, how do we make sure we actually hit that martensite state? I mean, it sounds kind of tricky. Well, that's where the secret ingredients come in, alloys. Think of things like chromium, which actually buys us more time during that critical cooling phase, or vanadium, which helps keep the internal grain structure fine and tough. You've got molybdenum for high-temperature strength, and manganese as a powerful hardening agent. These little additions are what make the difference between just plain steel and a high-performance tool steel.
Okay, now we get to the really dramatic part. This is where we forge the steel in fire and ice. It's a high-stakes trial of transformation.
The whole hardening cycle is like a perfectly timed three-act play. First, you have the preheat. This is a gentle warm-up to stop the steel from cracking from thermal shock. Next, you austenitize, which is when we heat it up to create that carbon-soaking sponge we talked about. And for the grand finale, the quench. This is that rapid cooling that locks in all that hardness, changing the steel from soft to incredibly hard.
Now, quenching isn't a one-size-fits-all kind of deal. You have to choose your weapon carefully. For some simpler steels with fewer alloys, you need a really fast, pretty severe oil quench to get the job done. The downside, there's a decent risk the part could warp or distort. But for the fancy, high-alloy steels, you can actually use a much gentler air quench. It's slower, but the risk of distortion is super low, which is absolutely critical when you're making complex, high-precision tools.
So at this point, success, right? The steel is super hard. But we've also kind of created a monster. It's all raw power, but it's also a brittle beast. We need to tame it.
And I'm not kidding when I say brittle. As the quote says, the tool is so fragile that it could shatter from a minor impact or even crack spontaneously. The internal stress is just so high that a small bump, or sometimes nothing at all, could make it literally shatter into pieces.
So how do we fix this? The solution is called tempering. It's a controlled reheating, but to a much lower temperature this time. What this does is it lets some of that internal stress relax. It's a trade-off, really. You give up just a little bit of that extreme hardness, but in return, you get a massive gain in toughness.
Let's put some numbers on this. Right after quenching, a piece of steel might hit, say, 65 HRC. That's the Rockwell scale. That is extremely hard, like glass hard. But as we just said, it's also dangerously brittle. But after we temper it, the hardness might drop just a little, maybe to 60 HRC. That's still incredibly hard, don't get me wrong. But now, it's also extremely tough. It can handle shocks, impacts, all the abuse of real-world work. That is the perfect balance we've been working towards.
But why temper twice? You might hear about that sometimes.
Well, with some high alloy steels, the quench doesn't convert everything. You're left with these little pockets of soft, unstable austenite. Here's the crazy part. The first temper actually transforms that leftover stuff into new, brittle martensite. So you have to do a second temper to take care of that new, brittle stuff. It's absolutely essential to make sure the tool is uniformly tough all the way through.
So as you can see, this isn't just one single process. We're really choosing the perfect recipe, tailoring the entire transformation to the specific job the tool has to do.
And matching the steel to the job is key. For example, a basic general-purpose tool steel like O1. It needs that fast oil quench. But what if you're making something really complex, where any warping would be a disaster? Then you'd go for an air-hardening steel like A2. And if you need something to take an absolute beating, like a die that needs extreme wear resistance, you'd pick a high-alloy air-hardening steel like D2. Different steels, different recipes, different results.
So after all that, we can finally answer our original question. What really gives a tool its strength?
And the answer is, it's not just the metal itself. It's the science of its transformation. It's that controlled, even violent journey that we put it through. This whole recipe of fire and ice is a great reminder that sometimes, to create real, ultimate strength, you first have to push something right to its breaking point. Makes you wonder, what else in the world follows that same rule?